Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video is going to look at using partial derivatives to evaluate thermodynamic properties. This has been prepared for the course Chemical Engineering 5220, Intermediate Thermodynamics. Specifically in this lesson, our goals will be to learn to use partial derivatives and differentials in combination with the first law to develop fundamental relations, and to relate partial derivatives using mathematical rules, and then to develop Maxwell relationships. So for a general open system, we start with the first law. Now this is a little bit of a different form than what we've seen. Instead of using like a mass or mole flow rate, we've done dN because I'm taking these as differentials rather than time derivatives. If you ignore the potential and kinetic energy, and if you just imagine that you could have a reversible way between state 1 and state 2, then what we're going to find is that I'm going to have the heat transfer is TdS, and the work will be minus PdV. This is going to be valid now for reversible and non-reversible processes. All of these terms are independent of path, and so therefore I do not need to consider a path, and so by imagining a reversible path, I actually got rid of the need to ever consider the path. I just have to consider the endpoints. Now, if you start with this and then take the fact that we have Gibbs energy as U plus PV minus TS, or H minus TS, and we can consider chemical potential energy to be the U plus PV minus TS per unit mole. If we do this, we get the energy form of the fundamental relation. So du is TdS minus PdV plus mu dN, that chemical potential. Now we haven't truly defined chemical potential yet in this course, but by introducing it now, I'm going to save myself a little bit of trouble later on. Now I can also solve this for ds because internal energy and entropy are the two variables that are kind of complicated in this expression. If you solve for ds, you get 1 over t du plus p over t dv minus mu over t dn. And again, we'll come back to mu, that chemical potential, at a later time in this course. So if you look at that fundamental relation written in terms of U, we know that U should be continuous and differentiable if it describes physical phenomenon that we're familiar with, which means that U is, according to this expression, a function of S, V, and the number of moles we have in our system. I can also write for a function of S, V, and N, the differential of U is how U changes with S while I hold V and N constant, ds, plus how U changes with V, holding S and N constant, dV, plus how U changes with the number of moles of each component, holding S, V, and the number of moles of the other components constant, dN. That's just a mathematical definition of a differential. Now these coefficients are process derivatives that are in the S, V, and N variable space. The numerator U is my dependent variable. Those denominators, so it varies. The first one is S, the second V, the last ones are N sub I. Those are my independent variables. When I put subscripts down here, that indicates the path. Those are the variables that need to be held constant. So if you compare these two equations, what you see is that T must be how U changes with S, holding V constant and the number of moles constant. And du dV at constant S and N sub I is going to be negative P. And chemical potential is du dN holding S and V constant. So these define our thermodynamic variables in terms of each other and process path variables. Now we're going to need some math rules. One of these is the triple product rule. And this is just a quick little derivation here. The triple product rule says that if you take a function of the variables y and x, then dz is dz dx at constant y dx plus dz dy at constant x dy. I could have done this in terms of any of the others, right? So I could have taken x as a function of y and z and written a similar sort of expression. So if I take the one for dz and the one for dx and combine these, I end up with this expression here for dz in terms of dy and dz. So I've eliminated the dx. And I can now algebraically rearrange this, combining the dz and dy terms, and then the coefficient of dz, okay, 1 minus dz dx at constant y times dx dz at constant y. Well, dz dx and dx dz multiply together to give you 1, so 1 minus 1 is 0. So what this tells me is that this other coefficient over here, this dz dx at constant y, dx dy at constant z, plus dz dy at constant x, must be equal to 0. And then we can algebraically rearrange that to get to the triple product rule. So the product of dz dx at constant y, dx dy at constant z, dy dz at constant x, when they multiply together, they give you negative 1. So we've developed these various terms here by using the definition of the differential. And we also have P over T is ds dv at constant u and n, and I can get that by doing the similar definition for ds. If you use the last two of these, let's see if we can combine them to recreate the first, just as evidence that the triple product rule works. And so, therefore, if we do this, I take the product of these two things here, du dv at constant s and n, okay, is negative p. I'm trying to get to p over t, so multiply by negative 1 over t. So negative 1 over t, du dv at s and n, is the same as this ds dv at u and n. If I now take that and multiply top and bottom by ds du at constant v and n, I have here my negative 1. This is a reciprocal, and we end up with this. So you're able to go through and manipulate things using this triple product rule to prove that things are equal to each other. Now in this case we were trying to prove something where we already knew the answer, but we're going to shortly be using this so that we can develop answers when we don't know the answer yet. We also have a second derivative rule. And this one is very important. For continuous differentiable functions, the order of differentiation is commutative, meaning you can do it in either order. In math, we call this Schwartz's Rule, but chemical engineers usually call it the Maxwell Rule, just simply because it's going to help us develop the Maxwell relations that are so important for us. So, if I wanted to do this second derivative, if I started with du dv at constant s and n, and then took the derivative of that with respect to s, that's the same as taking the derivative with respect to s of t, right? Because du dv at constant s and n is equal to t. On the other hand, du ds is equal to negative p. Take the derivative now with respect to v, I get negative dp dv is equal to dt ds. Okay? So this is going to allow us to change things that can't be measured into something that I can measure. The full set of Maxwell's, you can go through and develop these, but they are shown on the screen here. I recommend that you make note of these, figure out how to develop them on your own, but they're going to be very helpful throughout most of this course. So this concludes this video lesson. I thank you for your time.